So I'd like to turn your attention to another example of free fall, and that's the motion of satellites. Before we get too far into it, a quick reminder of what we studied up till now. One of the last things we left off with was the motion of a projectile launched across level ground. And I'd encourage you to see if you can recall some of the equations that we've derived that describe what's the maximum height, what's the range, and what's the time of flight if you know the launch speed and the launch angle for a projectile launched across level ground. The problem with this study is it's hard to find level ground unless you restrict yourself to short distances along the Earth's surface that for all practical purposes appear level. But of course, the Earth is curved, and so if you launch a projectile far enough, it's never launched across level ground. It's launched across the curved surface. Now, I hate to upset any members of the Flat Earth Society, but if you'd be kind enough to remove your tinfoil hats for the rest of this lecture, maybe you can follow along. Here's a picture that ought to confuse some of the flat earthers. You can see the sailboat and the top of its mast, but you can't see the rest of the boat as it dips below the horizon. I believe I have these numbers right. If a sailboat was any more than 5 miles out to sea, and its mast was any less than 16 feet tall, then it's guaranteed to disappear over the horizon. That is to say, for every 5 miles outward, the surface of the Earth drops 16 feet. Of course, we don't use these units of measurement. We like to stick to metric. So I think this is about for every 7.9 kilometers, the Earth's surface drops about 4.9 meters. Now, there's something special about 4.9 meters. If you look at the equation y equals 1/2 gt squared, 4.9 meters is the distance an object falls in its first second of free fall, right? 1/2 times 9.8 meters per second squared times 1 second quantity squared gives an answer of 4.9 meters. It's a common mistake to think that an object falls 9.8 meters in the first second of free fall. It only falls 4.9 meters, half of that value. Anyhow, that is to say that if you could project an object so that it went 7,900 meters, same thing as 7.9 kilometers. If something traveled horizontally 7,900 meters in a time of 1 second, the pull of gravity would want to bring it 4.9 meters closer to the surface of the Earth because of the nature of free fall, yet its projection makes it want to travel outwards 7,900 meters. Well, here, I can express what I'm trying to say a little bit better with this concept known as Newton's mountain. So there is no such thing as Newton's mountain, right? We name it that in honor of Isaac Newton, since we're in the beginning stages of our study of motion. And the reason we want to reference a mountain is we just want something that's tall enough that it sits up above the tallest trees or the tallest buildings or anything else, so that if we project something horizontally, now if we shoot something at a low speed, then it follows, hey, had this been level ground, we would have called that half a parabola. But eventually it will strike the surface of the Earth. If you throw something a little harder off of Newton's mountain, gravity's going to make it fall and hit the surface of the Earth. But you might be able to project where I'm going with this. If you could throw something fast enough from the top of Newton's mountain, then does it ever fall so that the way in which the curvature of the Earth falls below a straight line matches the way in which your satellite would want to fall? Yeah, this is absolutely how satellites are placed in orbit. They have to be projected with enough tangential speed so that the inertia, the desire to continue on in a straight line, combined with the pull of gravity acting straight toward the center of the Earth, that force pulls the object off of the straight line path as given by the law of inertia, and it pulls the object down onto this curved path due to the pull of gravity. So how fast exactly does something have to be projected tangentially? What does that tangential speed have to be? It has to be 7,900 meters per second. And then the object will have a combined desire to go in a straight line. So let's say now the object gets here, it wants to continue tangent to its path, but it doesn't follow that straight line path because there's constantly the pull of gravity, which takes it off that straight line path and falls back onto the orbital path. And then the object gets here, the law of inertia gives the object a desire to continue on this straight line path, but gravity pulls the object toward the center of the Earth, causing it to continue to fall inward toward the center. Now, if the speed were any less than that, then you wouldn't end up having a circular orbit. Let me paste the Earth here again. Oh, we brought along a little bit of a projectile with us, didn't we? Let's erase that. We can draw Newton's mountain. Yeah, if the speed is, well, more than the speed that would cause it to immediately crash into the surface, but less than the 7,900 meters per second of tangential speed that would allow for a circular orbit, you could have an object that almost crashes into the surface when it gets to the far side, just barely skims the surface, and then gains altitude again and comes back to the top. That would be an elliptical orbit in the case where the tangential speed is less than 7,900 meters per second. And of course, you could have a case where the tangential speed is greater than 7,900 meters per second, and then you'd also have an ellipse, but an ellipse where it's far from the Earth on the opposite side and then comes back to the top of Newton's mountain. But if it's just right, if you have that Goldilocks speed, so to speak, of exactly 7,900 meters per second, then you can place an object in a circular orbit. So there's something about these circular orbits. Any circular orbit is described by an object that has a desire. Let's put the Earth in here as well. Now, what was I saying? Any circular orbiting satellite represents an object with a desire to move in a straight line due to the law of inertia, being overcome by the force of gravity that's always pulling straight toward the center of some planet. So there's the straight line path as indicated by the law of inertia, but the object is actually on a circular path, and that's because there is a pull of gravity toward the center of the Earth. When the object gets here in its circular orbit, there's a pull of gravity toward the center of the Earth. When the object is here in its circular orbit, you got it right, there's a pull of gravity, straight toward the center of the Earth. No matter where the object is in its circular orbit, the pull, the force that's causing it to go in a circle, is directed at a right angle to the velocity it would otherwise have if it followed the law of inertia. So there's a tangential velocity that points in a direction 90 degrees off of the force that pulls toward the center. No matter where the object is, the instantaneous direction of the velocity vector is always at a right angle to the force vector. That's a key feature of uniform circular motion. So there's a word for vectors that point toward the center. We don't have to use this phrase, toward the center. We can replace that with this adjective, what do we say? Centripetal. I guess literally meaning center seeking. There's another word that sounds a lot like that. What is it? Centrifugal, right? Think about in your chemistry class when you try to separate the solids that form in solution from the rest of the liquid, you might put a test tube in a centrifuge. So centrifugal means center fleeing. So if there happened to be some sort of force that pointed directly outward away from the center of the circle, we would say that's a centrifugal force, but turns out there isn't a force like that. The whole reason why any satellite orbits around a planet is for sure due to the presence of a centripetal force. And force can be centripetal, acceleration could be centripetal. Any vector that points toward the center of a circle can be described as a centripetal vector. So that just gives us one example, this satellite motion and this thought experiment known as Newton's mountain gives us something to think of to link the idea of projectile motion with uniform circular motion. In the next unit of study, we'll describe uniform circular motion and derive a formula that says centripetal acceleration, or we can just always symbolize A subscript C, is equal to, well, it's a function of how great the tangential velocity is and also how large the radius of the circular path is. And the function goes something like this. The centripetal acceleration is equal to the tangential speed squared divided by the radius of the circular path. That's true for satellites that orbit around a planet. This is true for a planet orbiting in a circular path around the sun. This is true for, even if you had a car, if this was an aerial view of a circular racetrack, and there's a car driving in the counterclockwise direction around this racetrack, so at a given instant in time, its velocity vector points straight ahead, but the car ends up driving in a circular path. The only reason it could do that if there was a force of friction pointing toward the center of the circle. So we would say that that friction force happens to be a centripetal kind of force. And that force produces a centripetal acceleration with a value that has to be equal to the tangential speed of the car squared divided by the radius of the circular track. For any object that moves with uniform circular motion, here's how we calculate centripetal acceleration. So this is just a preview of an equation we'll be working with, and in the next video lesson, I'll try to derive that formula to provide a little greater understanding.